So recently I got my hands on these huge power transistors, FF1000R17. They are quite crazy, they are huge, and I got them for 30 euro. I have two of these and I got them 30 euro a piece. And every time you buy something off eBay for very cheap, you have to be quite suspicious, because if you wanted to buy these as a new unit, it would cost you a fortune. So how is it that they can provide these transistors at this 30 euro a piece price? It's quite crazy. Well, you really have to be suspicious, because these could be fake. You know, it kind of happens sometimes that when you order something, especially from China, it can be fake. These could be, you know, like some ordinary transistors just sitting in this casing, so it looks like a real deal, but it doesn't necessarily have to be the real transistor. So it got me thinking, like, if I wanted to measure just based on electrical characteristics if the transistor is the real one or if it's a fake one, how would we do it? So I don't really want to experiment with this transistor, so I don't want to break it off. So I found this one. This is some old BSM 100 GB. I don't know, it's an IGBT. It's like 20 years old, but it still can handle a lot of amps. And actually, I have 3D printed this. Now, believe me or not, but this is a transistor. And I want you, just based on the electrical properties, distinguish between these two. How would we approach it? Now, of course, you can tell that this one is fake, that this is not the real deal, but it is a transistor, and I will show you that it is a transistor, and I will also show you that based on the electrical characteristics, these two are pretty much indistinguishable. Now, of course, this one is fake, but let's forget about the physical appearance for a while. Let's only focus on the electrical properties. Now, how would we approach this problem? I've actually seen some videos on YouTube. You know, I don't really want to name anybody because I don't want to sound disrespectful, but I've seen a lot of videos where they show you how to measure if an IGBT is a real IGBT, and usually those measurements consist of like measuring the voltage drop between the collector and emitter, or measuring the gate capacitances and so on. And I want to prove to you that those measurements are absolutely worthless. They are pretty much the waste of your time. The only thing you actually get from these measurements is that it is a transistor, but it doesn't tell you anything else pretty much. So let's see what we get if we measure those basic electrical characteristics like gate capacitance and collector emitter voltage drop. So first, let's start by the easiest. Let's measure the gate capacitance. So let's take this IGBT, the real one, and let's measure its capacitance. It should be, according to the data sheet, something around 8 nanofarads, and it's like 8.6 nanofarads at 1 kilohertz. Alright, now let's test the fake one. If it's got like the similar properties or if it's totally different. And we can see 8.56. So yeah, this test didn't actually tell us anything, and we can pretty much scrap it. So let's go to another test. So let's go to another test. This is the test of the gate threshold voltage. So I have these leads from my power supply connected to this IGBT. One channel is between the collector and emitter, and this channel is between the gate. So let's slowly ramp up the voltage on the gate, and let's see at which voltage they will start to conduct. Alright, so 5 volts, 5.3, 5.6, 5.8, and I see some low current. And let's go even further. Yeah, so it was something like 5.7, something like that. And now let's see the other one. So the same setup, just with the fake one, collector, emitter, and let's slowly ramp up the gate voltage, and let's see what threshold voltage will we get. And it is roughly, you know, 4.8, 4.7, something like that. So, you know, it's basically pretty much the same. Like most of these transistors, they will have these threshold voltages in like around 5, 4, 6 volts. So again, this test, you know, it doesn't really prove anything. I can pick pretty much any IGBT transistor and the gate threshold voltage will be around 5 or 6 volts. Okay, now let's try another test. I have put 13 volts on the gate, so this transistor is fully turned on, and we got about 2 amps of current flowing. And now let's measure the voltage drop between the collector and emitter, and it's roughly 0.8, 0.84. Okay, so that's the collector emitter voltage drop. Now let's do this with the fake one. Alright, so the same test here, 13 volts at the gate, and this transistor is fully turned on, and we got 2 amps flowing. And let's measure. 0.835. That's even a bit better, but it's pretty much the same thing. So this thing has the same collector emitter voltage drop. So we got all these tests, and the gate capacitance pretty much the same, like 8.5 nanofarads. The threshold voltage 4, 5, 6 volts, and the collector emitter voltage, the same thing basically. So I imagine that some people would actually conclude that these have to be the same. Well, you'd be dead wrong, because this is actually just a basic, I don't know, this what is this, G4F something transistor. It's an IGBT, of course. It doesn't have the internal diode, so I've added one. And to simulate the gate capacitance, I actually added some basic capacitors. And yeah, this is it. This is just this transistor. And yet we couldn't distinguish it from this one. So what we did wrong in these tests? Well, some of these tests were actually wrong from the start, like measuring gate capacitance, that doesn't tell you pretty much anything. Most transistors have their gate capacitance in like nanofarads range, and sometimes the gate capacitances don't even really add up with the datasheet. Also measuring the threshold voltage, again, 4, 5, maybe 6 volts, that's pretty much standard for all IGBTs, whether it's like a big IGBT brick or whether it's just like a small TO247 IGBT. So those two tests are pretty much worthless. But the collector emitter drop voltage is actually a good idea. But the thing is that people do those tests at low currents, and at 1 or 2 or maybe 5 amps, those are low currents, and pretty much all IGBTs will have a very low voltage drop at these currents. So if you look into the data sheet, like this IGBT can actually handle like hundreds of amps, and the voltage drop between collector and emitter, it will still be like a few volts. Whereas if you look into the data sheet of this one, and you put like 100 or 200, 300 amps of current flowing through this little small package, it may even desaturate and destroy itself. So measuring the the collector emitter voltage, yeah, that's a good test, but you have to meet the right conditions. You have to test this at their limit. You cannot just get 1 or 2 amps flowing. You actually have to get into the limits of what these can handle, and then you will see if the voltage drop is the correct one, or if it's wrong. So let's do the collector emitter voltage drop test the correct way. Here I have 6.8 thousand microfarad capacitor, which is charged to roughly something like 49, almost 50 volts, and I will discharge this capacitor through 0.4 ohm shunt, and this way there will be a lot of current, maybe like 100, 120, 110 amps or so. And by the way, this current shunt is built such a way that it has the lowest possible stray inductance. I will give you a link to a video by a user called Vidduley, who actually describes why this is very important and how to build them. So this current shunt has an inductance of around like 4 nanohenry or something like that. So it's very small. And I'm going to discharge this capacitor through this resistor, and we will see what voltage drop will we get at very high currents. So let's just trigger the gate. Done. Discharge the gate, and we can see here on the oscilloscope that we have roughly 45 volts or something like that. And at this 45 volts we have, if we divide it by 0.4 ohms, we get something like 120 amps. So here we can see about 120 amps, and at this current the voltage the voltage between collector and emitter is roughly 1.7 volts or so. So now let's do the same thing with the other transistor. So a fun thing happened during testing. I actually killed the transistor. So as you can see, if I trigger the gate, you know, it's already short circuit, so if I discharge the gate, nothing happens. But I actually captured the last moments of this transistor's life. As you can see, it really doesn't like these high current pulses. It seems to oscillate somehow at around 100 amps. Yeah, that's really not good. Maybe the oscillations are caused by all these external components I added, like the gate capacitance. Yeah, but this transistor lasted for like 3 shots of this capacitor discharge. So here we got the first proof that this transistor is definitely not the real one. So another good way to test if IGBT is the real deal is to measure the thermal capabilities. So this heatsink should be, the real deal. It should be good. So what that means is that the heat from the die should be transferred to the heatsink very quickly, and it should heat up quite fast. Like if you load up this transistor, if you waste some power on it, I would expect this to get quite hot very, very, quickly. Whereas in this case, so I actually made a heatsink, it kind of doesn't look really good, but it is a heatsink. And it's made from like copper wires wrapped in aluminum, so it's actually not that bad of a heatsink. It actually conducts heat quite well. And let's see, let's waste some power on the transistor. Let's run the transistor in the linear region. So I have like 4.5 volts on the gate, and let's see if we can actually waste some reasonable power. So this is like 10 watts of power, and if I touch it from this side, this is stone cold. Yeah, but the thing is that the die of this transistor is now getting burning hot, but it's stone cold because it doesn't transfer heat very well. But now let's try the same thing with this IGBT. So again, the same test. I'm running roughly 10 watts of power dissipating through this transistor, and this, yeah, I mean, it's not stone cold. It's definitely like not hot. I mean, I would probably need way higher power to waste, but yeah, it's getting warm. I mean, I would probably do much better job if I took my thermometer, but yeah, I think I'm pretty good with guessing like temperature just based on the touch. And I would say this is like, I don't know, 35, 36, 37 degrees. It's basically like my, yeah, it's pretty much, that's very similar. So I would say right now it's like 37, slowly rising, 38 degrees. While this one was stone cold. So yeah, they cannot fake very good thermal conductivity between the die and the heatsink, right? And if they can fake everything, if they can fake the voltage drop between collector emitter, if they can fake the thermal conductivity, then at that point, well, you got 2 same transistors, so it's really not fake anymore. So yeah, I hope you enjoyed these tests, and I hope you liked this video, and in the future I might do more tests with IGBTs. I might even, do some tests on these ones, on these little babies. Let's see what they are capable of. And yeah, I hope to see you very soon in the next video.